Okay. Hello, everyone. Welcome back again. Today we have Dr. Tousik Samui. He will talk about quantization of the vector field or the photon field specifically.
Okay. My screen is visible, not yet, right? No, it is. Okay. So, let me start. We kind of have some introduction to the vector fields, especially the electromagnetic field, the photon field, mu, and we have already seen that how the Lagrangian for that can be written. Okay, so let me start from there. And today, the thing that I will discuss is basically the quantization of that field. Okay, so it will be similar to the quantization of a scalar field or the Fermion field, but it has some difficulties that I'll explain as I go along. Okay, so let us start with the field first. See that what are the problems arises when we try to quantize it. So let us start with the Lagrangian that we have derived, which is for the free field is nothing but this 1 minus 1 over 4 f alpha beta. So, and we are using Einstein summation convention, meaning that all the repeated indices are summed over. So here alpha, beta are summed over. Okay, and we remember that if mu or if alpha beta here is defined as del alpha a beta minus del beta a alpha, which is completely completely antisymmetric in alpha and beta indices. Okay, so with this, so first we will try to quantize this. Okay, so first step that we know that for the quantization, we need to find the conjugate momentum for the field M, right, or A beta here. Okay, so let us try to find the momentum conjugate. Okay, momentum conjugate, and the next step would be to promote them to operators, the field and their momentum fields, and appropriate commutation with appropriate commutation relations. Okay, so first try to find the momentum conjugate of mu. Okay, which we denote by pi mu, which is again function of x. Okay, so which we already know it should be del L over del mu dot. Here dot means del T mu, or in other words del 0 mu, right? So this, if we try to calculate it, let us calculate it, del 0 mu. Okay, so now remember the Lagrangian that we have all has so two term has downward index, two term has upward index, and since we're trying to take the derivative with the downward index here, so let us write down the Lagrangian in terms of the indices which are like downward. So that we can write in terms of alpha rho, eta beta sigma. So if alpha beta was already down, and the other two we can write this way. Okay, so now if we now try to differentiate, then we see that it will be nothing but eta alpha rho beta sigma. That's fine. Now we will differentiate it with respect to del 0 a mu in f alpha beta. So where f alpha beta is del alpha a beta minus del beta a alpha. So it has two terms. Okay. So box this part, and so this will pick up value when alpha. So from the first term, it will pick up value when alpha is 0 and beta is mu. So that can be written as alpha 0 delta. Sorry, alpha will go upstairs. Delta alpha 0. No, 0 will go upstairs. That's fine. Delta 0 alpha delta mu beta minus, from the second term we will have delta 0 beta and delta mu alpha. Okay, and with this we will have f mu nu, f rho sigma, and same thing will happen with the second term. Okay, beta sigma, then it will be if alpha beta, but now the derivative will go into the second term. So it will be delta 0 rho delta 0 rho delta mu sigma minus delta 0 sigma delta mu rho. Okay, so this is simple. And then if we contract now, that is like repeated in this indices are summed over. So this alpha here, for example, this alpha and alpha will contract. Okay, so this will give you eta rho 0 rho, and then this rho again contracts with this f term. So eventually it will become minus 1 by 4 if so alpha contracted, rho contracted only. So alpha rho in every place it will be replaced by 0, right? And then from the first term, and from this one, what will happen? Beta contracted, sigma contracted, and then it will be mu. Okay, and from the second term it will be just the opposite to this. Okay, and then 1 over 4 if here also will have 0 mu, and if mu 0. And interestingly, it will be finally minus if 0 mu. So that it will have. Now, if we see the 0th component of it, it's minus f 0 0, okay, which is 0, and by I, which is the 1 2 that I goes from 1 2 and 3, it's minus f 0 I, and if we remember the expression, it's nothing but the electric field. Okay, so now this creates a problem. Okay, so this let's say this one creates a problem. Why? Because we cannot consistently define any commutation relations for pi naught, because pi naught is exactly 0, and this we have already encountered. If you remember in our last lecture, that this is basically the consequence that a naught does not have this is basically consequence of a naught having no kinetic term. Okay. So that was the problem that we faced. Okay, but of course one can do one thing. One can choose a naught to be 0, just like we did yesterday, and define the commutation. Then this commutation will be exactly 0, and we do not bother about the a naught field anymore. Okay, and we will just quantize the theory with pi and appropriate commutation relations. That is one way to do it. And we as we explained the Coulomb gauge yesterday, Now, with that gauge, we can consistently do it. And I have given it as a problem in the problem sheet, and that you have to solve. All the steps are written. You just have to follow the step, and you can actually do the quantization. But today we will not do this way of quantization, partly because we have taken effort to make whole Maxwell equations into this covariant form, where time and space are on the equal footing. So this we want to quantize in such a way that we have manifestly Lorentz insane footing. Okay. So we want to quantize the theory. We want to quantize the theory, be it Lorentz invariance or Lorentz covariance manifest. So that is how we want to do it. But this way of doing that, if we set a naught to be 0 and quantize in terms of a i's and pi i's, does not have that equal footing of time and space. So we want to do this in a clever manner. And for that, instead of choosing Coulomb gauge, we will choose a different gauge, which is called the Lorentz gauge. And in this gauge, just like Coulomb gauge, we have one condition. The condition that we'll be imposing for this gauge is a a naught equals 0. Okay, so this is the condition that we will put. And similar to previous, yesterday, if let's say somehow this is not 0, we can always make a gauge transformation. Let's say a mu, or let's say a mu, a prime mu is a mu minus del mu of lambda. So if let's say del mu, a mu is not equal to 0, but it is equal to some function a. Okay, so if that is the case, then we will do in such a way, and then we demand that a prime mu to be 0, which is nothing but del mu a mu minus del mu lambda. And now if we, so now this is if so del mu lambda, and we will choose such a lambda so that del mu lambda is f. Okay, so this way we actually can choose. So now if we somehow are in a different choice, we can always make a transformation and always choose this condition. Okay, so that's how it works. So we can always choose the Lorentz case. Okay, so that is one thing. But just notice that in the Lorentz case has already so since it is a mu del mu a mu equals 0, it already has some Lorentz covariance manifested. Okay. So you see that all the indices mu from 0 to 3, all the indices are on the same footing. Okay, so this already is an improvement towards the Lorentz invariant way of quantizing the thing. But another important thing that I want to discuss is that even in this Lagrangian that we wrote has another problem, okay, which is some alternative problem. So the Lagrangian that we discussed as 1 over F alpha beta, F alpha beta. So this gives rise to Euler-Lagrange equation or equation of motion. Equation as you remember, it should be del alpha if alpha beta equals 0. Okay, so now if we expand this as del alpha a beta minus del alpha del beta a alpha is 0, and let us try to massage this equation as del alpha beta rho, and let us bring the rho downstairs because this is basically a beta. And similarly, this from the second term we do uh, another eta rho as a rho to be 0. Okay, so now if we massage this equation, we can see it is rho beta, and this, if you remember, is nothing but the box operator. Okay, so this is box operator, which is del t square minus nabla, and then this will become del beta del rho, and acting on a rho to be 0. Okay, so now if we notice, this operator is actually a singular operator. So the problem with this singular operator is that we cannot invert this operator, and hence it's difficult. Uh, it's not possible, or let's say difficult to invert this operator and get could get a Green's function. And we can see that this is a singular operator if we actually try to expand a rho in Fourier modes. Then this is very, very apparent. Let's say this we can write in the Fourier mode as epsilon rho, and let's say this is p to the I p dot x. Okay, so this is, let's say, a typical solution of this equation, and where we have already introduced that this epsilon is nothing but polarization vector we have introduced. Okay, so now if we actually calculate this operator, all the derivatives will basically become the momentum, and then if you actually calculate this operator, O beta rho, let's say we define this operator to be beta rho box minus del beta del rho, and in the momentum space it will be nothing but beta, let's say beta, so beta, and this will be minus p squared, where p is the momentum, plus p beta p rho. Okay, so just we have lowered the indices to make our writing convenient. But other than that, it's the same thing. Okay, so this becomes, in the momentum space, this becomes this, and if you actually see this operator, let's write it as rho beta as a matrix form, then you will see it will be p squared plus p naught squared, and then p1 p0 p2 p0 p3. Okay, and we'll have p squared minus p1 squared, p1 p2 . V2 squared and V2 V3 and then V3 V0 V3 V1 V3 2 and V squared minus V3 squared. And if you now actually calculate this thing, the determinant of this operator, you will see that the determinant is actually 0. Okay, so then what happens that we cannot invert this equation and get a good that's a Green's function. Okay, so that is another problem even if we try to quantize. But the solution is that if we go to the Coulomb gauge, we can consistently do it with certain tricks and we can avoid this problem. Okay, but thankfully we have a different prescription where we have thankfully we have a different prescription with one Lorentz covariance dynamic and phi naught not equal to 0, which was a problem, and third date is not exactly this operator will appear, but date or with non-singular operator, non-singular operator. Okay, so we already have a thing that will satisfy all these things, and that is via the Lorentz. So let us now rewrite the equation of motion. Let's say in Lorentz gauge, with Lorentz gauge condition, it will be again if we write it, we already have written it. So this one, okay. So this one is del alpha beta del beta. Okay. So del alpha a beta minus del alpha del beta a alpha. And now if we see this term is 0 del beta del alpha, and in the Lorentz gauge this is 0 in Lorentz gauge. And then in the Lorentz gauge we have a very simple looking equation of motion, and which is this. So this automatically solves one Lorentz covariance problem and non-singular operator that we were getting if we choose Lorentz gauge. But this does not solve the problem yet as of now, this pi not equal to 0 problem. Okay, so for that what we will do, we will change the Lagrangian by noting that in the Lorentz gauge del mu mu is 0. We'll change the Lagrangian to something which has del mu mu, and in the back of our mind we will like remember that condition is there, and then we will see that how that can be that problem can be avoided of adding the extra term. So but the prescription is we will modify the Lagrangian to -1/4 a alpha beta, and then half del alpha a alpha its square. Okay, so this is not exactly Maxwell's Lagrangian, but this will give us the same equation of motion as the equation of motion of the Maxwell's theory in the Lorentz gauge. Okay, so so let me give it an exercise that this L, the modified L, let's say, modified L, modified gives Euler so beta equals 0. Okay, so this will automatically give, even without imposing the Lorentz gauge, this will automatically give the equation of motion to be this. So now if we see this equation of motion, we can actually see that this equation of motion is a very familiar equation of motion. So this is nothing but this equation of motion is similar, or exactly same actually, similar to the equation of motion of a scalar field. Okay. Scalar field. Except that we have four such equations. That is the only thing that we have. The beta equal to 0, 1, 2, 3. We have four different equations, but all the equations are actually similar to the uh, to the scalar field. So usual mode expansion will be similar to the scalar field, except that we now have to calculate the momentum fields, the conjugate momentum field with the modified Lagrangian. So now, if we try to calculate, so for the quantization, we first have to find the momentum operator, and let us try to calculate the momentum operator here. Okay, so the pi mu is again with del L, let's say this modified, divided by del of del Z over del A mu, right, that we have. And we already know the first term is F0 mu, right? So that we can see somewhere here. Okay, so pi mu, as we can see, is nothing but minus F0 mu. Okay, so from the first term, it's obvious, and from the second, we will do it in the same way as we did before. So it will be, let's say, del 0 A mu. Okay, so now we will have the term of let's say half comes here, and then we will have, let's say, del alpha, A alpha, del beta, A beta. Now, what we have to do is lower these indices. So we have to introduce eta metric so that we can lower the index. Okay, so let me introduce that eta function, eta metric, so alpha. So this is fine. And then in order to lower this one, let us introduce another eta, which is beta sigma. Okay, so this is nothing but F0 mu minus half del of del 0 A mu. Okay. Okay, so let us take the derivative itself, and it will be, let's say, from the first term, it will be delta 0 alpha delta mu rho, and then we'll have del beta A sigma as it is, and then eta alpha rho eta beta sigma. And from the second term, it will be del alpha A rho as it is, and delta of 0 beta delta of mu sigma, and eta alpha rho eta beta sigma as it is. Okay, so this will be minus f0 mu minus half, and then alpha contracted, uh, rho contracted, so it will be okay. So alpha, so in place of alpha we'll have 0 here, and in place of rho we'll have mu here, right? So del beta A sigma, and then we'll have eta 0 mu eta beta sigma, and then from this we'll have the similar thing del alpha A rho that will remain here, and in place of beta we'll have 0, in place of sigma we'll have mu. Okay, so eta alpha rho, and it will be eta 0 mu. Okay. Now it will be half. Okay, so eta 0 mu will be common to both, and then it will be del beta A beta plus the other term will be del alpha A alpha. And so these are repeated indices, so alpha beta does not mean a specific thing. So this is also summed over of beta and summed over alpha, so these are basically essentially the same thing. So it will be essentially f0 mu, and the two factor goes away, so it will be 0 mu and del beta A beta, right? So that's the thing. And then the pi, then the 0th component would be minus f00, which is actually 0, and this would be eta 00 del beta A beta, which is nothing but minus del beta A beta, since eta 00 is 1. Okay, and pi I, the other components are nothing but f0i, and since eta 0i are 0, it will be the same. Okay, so these are the two so let me write it again, del beta. So these are the two momentum conjugate that that we get now. Okay, so now the next step would be to quantize, would be to introduce appropriate commutation relations. Okay, so let us introduce that. That is first commutation relation that we get is a mu y, and so a commutation relation and momentum commutation relations, we know that they should be 0, right? So they should be 0, but so that's the thing. And with the momentum we say that the commutation relation will be I eta mu nu delta 3 x. So this this quantity eta mu nu already says that the commutation relation that we set is in a Lorentz covariance manner. Okay. Covariance manner. Okay, so this is the Lorentz covariance that that we introduce in this set. And now the next step would be we have to let's say mode expand this mu into the creation and annihilation operators. So now let us expand as usual. So these are the steps. I'm fast forwarding it, but these are the steps that Ratul already discussed in very detail. So I'm just fast forwarding it, assuming that these steps are already understood. Expand or let's say right a mu. By the way, what is the time now? Okay, so I'm go to time, or is it late? Let me write this mode expansion, and then maybe I will stop for question and answer. Okay. This is the usual mode expansion that we had in the case of similar to the case of scalar field. Okay, where you can actually identify that this is nothing but the omega p that that was introduced by Ratul, and this for this case it is nothing but mod of p. Okay, and also this lambda, epsilon lambda are the polarization basis vectors that I introduced you yesterday. Okay, so just remember that in this formalism, since at least here we are not removing the degrees of freedom by hand, there are four polarization vectors. So at least here we have four polarization vectors. Okay. So now maybe I can stop for question and answer, and then I'll
sure.
Detailed on the polarization vectors in the next part. Okay.
Yeah, sure. I'll pause the recording.
Okay. So as I was explaining that, okay, with the commutation relations, let me write them again here. Then x and y. So these are trivial because these are 0. Should be 0. These are the equal commutation, equal time commutation relation, and for a mu x with its conjugate momentum, that is given by eta mu mu, and so this eta mu nu actually tells that we have Lorentz covariance that we already discussed, manifested in it. Okay, so now as I was saying that we have this mode expansion now that we also did in the scalar case in terms of its momentum and creation annihilation operator by integrating them out with this as square root 2 over mod p. Okay, and now notice that I'm writing a summation from 0 to 3, which is basically 4, with four components as a lambda p x minus a lambda dagger p minus I dot x. Here, let us notice few things here. Okay, so first of all, there is a sum. There is a sum over lambda from 0 to 3, 0, 1, 2, 3. Okay, so what are these? These are called polarization vectors that we introduced yesterday as well. So yesterday we saw that out of the, so mu has 4 components. Out of these 4 components, 2 are independent and 2 can be traded off with the gauge invariance symmetry. Okay, so we had only 2 degrees of freedom there, and that is why in that we can choose we could choose 2 polarization bases. Okay, but here we are not imposing the Lorentz invariance in the operator. Rather, we will do it in the Hilbert space. Okay, so that's why we have here we have 4 polarization. Okay, so lambda goes from 1 to 3, and so let us choose some of the basis vector. There can be some different choices for you also, but let me show that some of the choices could be, let's say, for photon field as not p0 0 not p. Let us choose epsilon 1 to be 1 0 0 0, epsilon 2 to be 0 1 0 0, and epsilon 3 so and epsilon 2 to be 0 mod 0 1 0, epsilon 3 to be 0 0 0. Okay, so epsilon, if you remember, epsilon has one index lambda and another index mu. What does these represent? So this lambda is which basis vector we are choosing, and this mu index actually represents which component we are choosing. For example, epsilon 3 2 would be 3 is our third basis vector, and 2 is the second component here. Okay, so this would be basically 0. So when we read epsilon lambda mu, meaning that lambda represents the which basis vector we're choosing, and the mu represent which component we're choosing. So that's the convention. And another normalization. So once we have all these basis vector, we can choose our normalization appropriately, and that also we want it to be in a Lorentz covariant way. So we want our normalization to be epsilon lambda dot epsilon lambda prime to be eta lambda lambda prime. Remember, lambda though is not the index that with which we iterate over, but lambda also has the four indices. Okay, so this can be actually chosen. So now with this choice, you can see that epsilon 0, epsilon 1 that I chose, it automatically satisfies this condition. So this is the normalization, just like orthonormal condition we chose. This is a slightly different. Here it basically says that epsilon naught is time-like vector, but epsilon 1, 2, 3 are space. Okay, so this is what we choose for our thing. But with this choice, let me point out that p dot epsilon 1 equals p. So when it is dotted with the momentum, okay, dotted with the momentum, it's 0. So just like yesterday, epsilon 1 and epsilon 2 are chosen to be to the momentum. So that we can always choose even with this condition. And also with this choice, we can see that P dot epsilon 0 is, if we calculate P dotted with epsilon 0, it's nothing but mod P. And this is seen as minus P dot epsilon 3. Okay, so this P dot epsilon naught and P dot epsilon 3, they are related by a negative sign. So these are the two important conditions that we'll be using later also. So we can always choose. So now if we want to go to a different frame where P is not exactly in the Z direction, we can always do that by appropriate Lorentz boost to the P as well as the same boost on all the epsilons. Okay, and thereby we will get a consistent polarization vector where we still have these conditions intact. Okay, so these conditions intact, since the dot that we are defining here is the dot with the Lorentz metric. Okay, so that is the way we should read this. Okay, and second point. So this was the first point. Okay, so point number 1, and second point, around this polarization vector, we have defined the creation and annihilation operators here. Okay, so that's the thing, that we have actually defined creation and annihilation operator for the particular polarization. So A so A so A P lambda. Okay, the scalar field, we did not have this lambda in there, so meaning that it is a creation operator, or maybe that's a different way we can say creates state with momentum P with polarization lambda. So earlier in the scalar field theory, we did not have the polarization. So it only creates the particle or the state with its momentum to be P. But here we say that it creates a state, but along with a specific polarization. So E dagger E on the vacuum that is denoted by 0 will give us a particle P, but along with it will give a polarization of that particle as well. Okay, so that's the thing, and similarly A P lambda annihilates state with momentum and lambda. Okay, so that's the thing. That is the second point that I wanted to stress. So now we are so once we identify that from the scalar, the difference is we have different polarization, and hence in order to span the whole space omega, we need 4 polarizations, and around that we create and annihilates. Mode expansion is around that creation and annihilation operator. Okay, so now with this, let me copy this. So now with this, let us calculate pi mu x. Okay. So it's not very easy actually to calculate pi mu, because pi mu has different expression for different things. So pi, if we remember, pi 0 is nothing but minus del mu m, right? So this is pi mu, and then if we actually with this mode expansion, so with this mode expansion, if we want to see what will be this thing, so then it will be minus and and this derivative will bring down p mu from the exponent, right? It will be sum over lambda equals 0 to 3, and it will bring down mu and epsilon mu lambda, and then we will have a lambda p to the power r p dot x minus a lambda p. But we'll have one plus I here with the delta. Right? Yes. Okay. So now, if we see that this is so just like scalar case, this is no longer a very easy form. But what happens that out of these, okay? So this, if you remember, this is basically P naught epsilon not lambda plus so minus or plus I epsilon I lambda, right? So now the claim is that only this will survive, this will the contribution from this will go to 0. Why? Because remember that the integration is from minus infinity to plus infinity. So minus to plus, and pi is actually is antisymmetric in, so if we change pi to minus pi, it picks up a negative sign, right? And because of that, so for any function which has this property, if x is equal to minus f of minus x is, so we call it odd function. So when we integrate from minus to the same limit to the plus, we know this becomes 0, right? So this becomes 0. Sorry, the integrand becomes 0. So that is why this particular thing actually will not contribute, because this forces the whole integrand to be odd function. Okay, so that is why only from the pi naught only only the p naught term contributes, and in the case of massless particle, this p naught is nothing but mod p. Then we can write it as plus I of mod p divided by 2 sum over lambda equals 0 to 3 epsilon naught lambda p, and then we have the user a lambda p. So this is the expression, and then if we write pi ix, okay, so pi ix has pi ix is nothing but f0 I is nothing but minus del 0 ai minus del I ac. So now, in the similar way, this del I will give rise to pi and which will be odd function, and then this part will not contribute, and if we actually calculate, it will be similar to the pi 0x, except that the index now will be, instead of 0, it will be I. Okay, so now if we actually write the whole thing down in terms of mu, it will be nothing but minus dqp I, and then we'll have mod of p over 2, and then we'll have the summation from 0 to 3, and the expression finally boils down to epsilon mu lambda and p, and then we'll have lambda, sorry, the annihilation operator I p dot x. Oh, another thing I forgot to mention is that this field is actually real field, so that condition of same operator a and a dagger has already been imposed. Okay, so if it were like not a scale, not a real field, it's a complex field, then this would have been like a, and this would have been b, something different. Okay. So that has already been imposed. So now I give this as an exercise. It will be similar to the scalar field, that from the commutation relation, between the fields derive commutation relations for the relation. Okay, so this will be the same. I will not derive this thing because this takes a little bit of time, and I will give you the answer, and you can take it as an exercise and derive this. It will be the so if you see the expression and mode extension, it will be the same, similar to the one in the case of scalar field. Okay, so the answer is the commutation relation will be essentially a lambda q lambda, the same momentum, let's say lambda prime is same as so the usual one. So creation becomes 0, but only surviving thing is creation with the annihilation. So it will be minus beta lambda prime. You may need some results from earlier that we derived epsilon lambda prime is eta lambda, so eta lambda prime. So that we might need, but otherwise it's the same as the scalar fields. Okay. So this is the commutation relation. If you calculate, you will get this thing. So once this is done, our half part of the quantization is done, but we still have to remove two of the 2 degrees of freedom that we saw. Before that, let us see that since space and time are on the equal footing, but they have a relative minus sign that we already. So now if we see this for the 0th component, Okay, so that is what is the commutation relation for zeroth component is nothing but this gives us 2 pi whole cube delta q. Okay, so this is the q and and um, this already is a problem because there is a negative sign. Okay, so why this is a problem? Because let us create a state. Let us create a zero polarized state. Zero polarized state. Okay, so let us create this state. So with momentum, some momentum. Okay, so then we can actually create this state with a0 p and that taking a dagger 0. So let us the state be p and polarization is lambda. So PAC. So this we can actually create. Now if we actually take p and 0, say with let's say some other state 0, you can see this will be nothing but 0. So this is created from this. Let's say from the vacuum, so it will be A0, B. Okay, so this whole thing can be written like this. It's the same equation here, but with Hermitian conjugation. And the other side, let us say this one is simple, which is A0 dagger U and from the vacuum. Okay, so now if we use the commutation relation between these two with appropriate sign, then it will be what? It will be A U 0 dagger A U 0 minus 2 pi of Q delta. So, and the first term, of course, the first term, let's say this one, of course, annihilates the vacuum. And so the contribution of this term would be 0. But what the second term gives us is a negative. So this gives us a negative norm state. Okay. So if P and Q are same, then we get a terrible negative sign. So even with the same state, we are getting the norm of the state to be negative, which is not a desirable thing. Right? So we have to cure this thing. In addition to that, we had the problem of 4 degrees of freedom, which are not really relevant. Thankfully, again, there is a prescription or a solution by which we can do that. So the prescription says that create all possible so or form the Hilbert space loans. Is there any question or something? form the Hilbert space as usual. So from the uh, vacuum state, you, let's say, create lambda dagger, a lambda prime q dagger, the way you want to create the Hilbert space from the vacuum, all possible state by this. Okay, but impose the condition that the physical states are those which satisfy uh, satisfy the condition del mu a mu plus okay, let me write it in the next psi equals 0. Okay, and where a mu plus is nothing but the plus of the expansion. Okay, so that's like this plus. So we had plus here, so with the annihilation operator. So let me write it explicitly that this is dqp pi 1 and one over square root here should be stairs and lambda p to the minus 30. So not should be plus x. Okay. So the first part, so this the type of convention Ratul already used that whichever comes with e to the power plus ix, we call it, let's say, mu plus. And so the Hilbert space, the usual way we create is creating the space from the vacuum with all possible momentum and uh, and polarization configuration, whatever you can do. Okay, but then you impose the condition that I will take the subset, not the whole space that I have created, the subset which satisfy this condition, and then if it can, if this is satisfied, then the collection of the collection of such states which satisfy satisfy the condition are actual physical states, and other states we don't care about. Okay, so that's the thing. And let us see that what this condition, so this condition has a name. This condition is called Gupta Okay. So what it gives is the following. Let us now see that del mu a mu plus psi, if we write, so this is nothing but p and this one equals square root 2 p, that is already there, and sum over lambda equals 0 to 3. 7 lambda in lambda. And acting on the state psi. So let us call this as a physical state. Okay, physical state, and this is physical state, and hence this. So this. Let us write this down. Okay, so now remember that we can always choose p p dot. So this is, let us write it again here. So this one is nothing but p dot epsilon lambda, right? And we have already chosen that p dot epsilon 1 and p dot epsilon 2 to be 0. Uh, to be 0. So here only third and only p0 epsilon 0 lambda and p3 epsilon sorry, dot epsilon 0 and p3 p dot epsilon 3 would only contribute. Okay. So then the sum becomes square root p, and it will be p dot epsilon naught a naught p plus p dot epsilon 3 a3. And now remember that we also have the condition this to be negative of this equals mod of p. That we can see here. That is that we can see here. Okay. If we impose that, then it will be so this is nothing but mod p, and this is nothing but minus mod, minus of mod p. Okay, so that comes out, and then a naught p, where a naught is the annihilation operator for annihilating a particle with momentum p and polarization 0, and a p. So this is the third component of the polarization, or the longitudinal component of the polarization, and e to the power I p dot x times psi physical. So for any physical state, in the Hilbert space, okay, we have effectively this condition. Okay. If it is a physical state, then we have this condition. This immediately tells that we have a time-like component and a longitudinal component, and our physical states are only those states which has exactly equal number of longitudinal and time-like components. And so this goes by the name of longitudinal component, because this is along the direction of okay. So because this is along the direction of the momentum, and this is of course the time life because this is the 0th component. Okay, so this immediately tells that our physical states are those which satisfy this condition, and they should have equal number of longitudinal and transverse component which actually cancels each other. So that is how we are actually getting rid of the extra degrees of freedom that we introduce by not choosing a particular gauge. Okay, so we introduced with four uh, four polarization vectors, but only two of them would be contributing to our any physical gauge invariant physical quantities that we'll be calculating. Okay, so that's the essence, that we are now restricting our Hilbert space. Only the subset of the created Hilbert space will be physical Hilbert space, and on which we will do all our calculations. Okay, so if that is the case, then you can see that even though uh, we did not put this condition as an operator condition, but any physical state, okay, uh, even if it is psi prime, and del mu a mu psi should be 0. Okay, so even if it is not put as an operator condition or in the field condition, but when we insert the Hilbert space, this can be seen very easily in the physical Hilbert space. Then this, let me see. So this is del mu a mu minus plus del mu a mu plus and psi physical. Okay. So now uh, this of course will by the Gupta-Wheeler condition, this is 0. Okay, but on the other hand, if you take the conjugate of it, then this side is also 0. Okay, so by this we can see that for any physical state, even though it is not put as an operator condition, but when we are inserting it inside uh, this this becomes 0. This is, let's say, kind of weak Lorentz gauge that we have chosen. Okay, so that's how we actually quantize this theory. And then once we do this, then we can now try to calculate the propagator that will be useful for this. And then the propagator can be calculated as follows. So this is the time ordering. So this mu nu x, and what's the time now? Sound really, and I'll not calculate the propagator. It will involve the same steps that Ratul did for just here. It will be just for the massless condition, and it will be essentially d4p pi whole cube whole to the power 4 minus I become mu p squared plus I epsilon. So this is not the same epsilon that the polarization represents. Let's write it as xi and to the power minus I dot x minus, so this should be y. And I leave this as an exercise. Okay. So this will involve the same thing that you did for the scalar case. Now, if we look at the Hamiltonian, okay, so that also I'm not going to calculate. Okay. So the Hamiltonian is the same usual procedure, and so the Hamiltonian, but with normal ordering. So normal ordering. Uh, let's say normal is of course this minus pi mu minus L, and from this we can actually calculate the Hamiltonian and giving you the expression, but I recommend you to do the exercise, this exercise at least, so that you can get a feel. That's the problem that is having. It suddenly stops, and okay, so let me Hamiltonian. Sorry about that. My iPad is actually behaving strangely, and that is why I could not actually prepare the lecture notes and send it to you. I had to. Okay, so that I'll try to send. It suddenly crashes and gets erased. Okay, anyway, so the Hamiltonian, let's say normal ordering, is given by pi q, and mod of p, it's the same as omega p, which is in this particular case is mod p, and it is 3 AIP. So this is normal ordering. The dagger operator, the creation operator is on the left, and other operators, annihilation operators are on the right. Okay. So now A0, dagger A0. And notice this negative sign that will be useful, because once we, let's say, calculate any expectation value with the physical state. So this, let me say it is exercise. Then with the physical state, let's say physical state, the psi is psi. Of course, we'll have some transverse component which are fine, but in addition to that, if we see that it will have psi A3 dagger E A3 minus A0P A0P and psi this side. So this is physical and this is physical. And now remember, so this is dagger. Now remember okay, so that equation is no longer there, but let me write it again. The Gupta-Boiler condition said that if it is a physical state, then this and this are equal. Okay, so for any physical state. Okay, and so with this condition, we know that this part, okay, is nothing but A3. This is equal to A3P, the third component of psi physical, and this with this will give me again A3. that's the thing. And then so it need not be side end, it can be side prime as well. Okay, and so it will be transverse part that it will be there. Okay, but this part, the longitudinal uh, uh, and the timeline part actually cancels and gives us a big zero. Okay, so only the transverse component will contribute in any physical system. So that's the beauty, that even if we don't impose the transverse condition in the operator or the degrees of freedom, but we can actually be were able to modify the Hilbert space in such a way that we say that, okay, the whole Hilbert space that we could create is not relevant. Only the physical part is that satisfy the Gupta-Bleuler condition is our Hilbert space, physical Hilbert space, and there we can see that this is fine. And further, which I will not prove, that for any gauge invariant operator, uh, will 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 operator evaluated on or independent, or maybe longitudinal. Let's so this is the thing. That's how we do it, and then the propagator has also been introduced. Now I think I'll stop here for more questions and answer, and then I'll continue the interaction picture, how these propagators and all this formalism that we developed, Ratu and I, could be useful in actually calculating some of the things that we can see in the experiment. Okay, so that will be the next two lectures, where I'll introduce you to the interaction picture, how the interaction works. Till now, we actually talked about free fields and their quantization, and then how interaction works, and then how do we do the calculation for certain things, like, for example, scattering or other things that we'll try to cover in the next two lectures. So yeah, so now I will take some questions. And
Okay. Thank you for the lecture. I'll stop the recording.